second semester master's student in data science, and I'm going to talk about my term project for time series analysis and modeling named Ozone AQI forecast. So we know that the air pollution is a serious environmental concern and ozone layer is a crucial marker for air pollution quality. The objective of this project is to perform a thorough time series analysis of US air pollution data with emphasis on O3AQI as a dependent variable with three important pollutants, that's nitrogen dioxide, sulfur dioxide and ozone monoxide. I have made use of different models to identify pattern trends and possible correlation among all the variables, and I started that with data cleaning, downsampling and made use of methods to test seasonality. I have created dashboard at the end to thoroughly access the air quality across all the addresses provided in the dataset. Now let's talk about the dataset that I have used. So the ozone AQI forecast dataset is a seasonal pattern multivariate dataset with 20 variables and 647,252 observations, in which 16 are numerical features and 4 are categorical features. I have filtered data by unique addresses having more than 5,000 observation, and I'm going to do analysis on one such addresses with a time span of 2000 to 2022, and the frequency of date is daily. Now let's talk about variables, and my dependent variable is O3AQI, and these are the list of independent variables my categorical variables are address, state, county and city. Now let's do a data cleaning to check whether there is any missing observation, and looking at this we can see that there are no missing values, but when I check the date range of the observation there are some missing dates. To fulfill that, I have made use of the drift method, and after that I can see that the number of observation are same for date range and the data filled data set, and these are some basic stats for dependent variable. Now let's talk about one hot encoding, where we used it to convert our categorical variable to numerical ones, but looking at our categorical variables all looks to be constant and we can avoid this step. Now let's talk about downsampling. Since our original data is sampled daily, we can do downsampling to weekly frequency, and here is a plot for weekly sample data versus timeline. Here we can see that the number of observation of weekly sample data is getting low, so we are going to stick with the daily sample data. So this is a plot of dependent variable versus time on the left. You can see drift fill data, and looking at the plot I can say that there is high seasonality in the data, so we can perform some seasonal adjustment, which you can see on the left, the de-seasonal data plot versus time, where again I can see that there is a seasonality included in the data. Now let's talk about ACF and PSCF of the dependent variable. Looking at the graphs, I can say that the ACF has tail off and the PSCF has cut off at leg 1. This is a correlation matrix of dependent and independent variable, and I can say that O3AQI has a high correlation with its respected matrices, and it works similar for the other variables as well. Now let's split the data into train and test with 80% and 20%. Let's see the seasonality using ACF, PSCF, rolling mean and variance, and ADF and KPSS test. From the plot of rolling mean and variance, I can say that the number of observations are going up, which indicate that the dependent variable is stationary. And at the same time, in ADF test, the p-value is 0. That indicates that we can reject the null hypothesis, and the dependent variable is stationary, and this works similar with KPSS test, but here the p-value is greater than 0.05. That indicates that we can reject the null hypothesis, and in general I can say that the dependent variable is stationary. Now, let's see our time series decomposition plot. From that, I can say that the strength of trend for this data is 76.74, and the strength of the seasonality is 4.8. And on the right, there are detrended data and the seasonal adjusted data plots, from which I can say that the seasonally adjusted data looks almost identical to the original plot that we have used, and data is highly seasonal. Now let's talk about Holt-Winters method, and here are 4 different methods. From the plots, I can see that the seasonality trend and the forecast is matching to some extent. This is a performance comparison, and from the value of RMSE, I can say that the Holt-Winters additive model with seasonal and trend component works best for us. Let's talk about feature selection using 3 methods. The first method is maximum adjusted R square. On the left, where it shows the list of features that is recommended to be removed, and by removing it we can see the change in the value of adjusted R square, which is getting maximized. And on the right, the plot of adjusted R square forecast, I can say that the test data and the forecast is matching to most of the extent. Let's talk about the second method, that wherein we check the p-value, and from the model I can say that the number of features is removed using a p-value which is less than 0.05. And the third method is BIF method, which works in the same way, by removing features which got value less than 10. This is a comparison of all the 3 methods, and from the value of RMSE, I can say that the adjusted R square with a value of 8.553 works the best. So let's talk about the base models, which includes 4 models, and none of the model captures seasonality in the data, so the error for the forecast will be higher than the other models which captures seasonality. And this is the comparison, and from this I can say that the average method with RMSE of 19.9 work is the best forecast method. So from step 10, we chose adjusted R square method as our best one, and on the left there is a complete regression analysis, and on the right there is a one step ahead prediction of my model, where I can see that the test data and the prediction is matching to most of the extent. Let's talk about hypothesis test analysis, which include F test and t-test. The t-test p-value is little high at 0.067 and 0.006. However, the f-test result is 0, so the model is still significant. Now I'm performing cross-validation for time series by 5 splits, and for my adjusted R square model, which will help me to verify my forecast function works evenly across the dataset. All this error matrix looks close to 8 as per step 10, and RMSE of cross validation is around 8, so the results are consistent using this model. This is a summary of my model, where RMSE is 7.215, and this is a ACF of residual, which looks like there is a white noise, but I can verify it later on performing residual analysis. And here it is a Q value and a variance and mean of residual. The Q value is less than Q critical, that indicates that residual is white noise and the model is good. This is a plot of train test and predicted values, and it looks like accurate with some error. Having said that, I'm going to make use of weekly data since since I have tried de-seasonalized data, but it looks seasonal and the model forecast is not good fit for this data. So that's the reason I'm going to use weekly data in order to reduce seasonality index of the dependent variable, and I think it's going to work pretty well using Sarima model. Estimated parameter using LM algorithm are as follows, and I have picked two orders based on JPEG table. This is ACF PSCF graph, and along with my JPEG table, wherein I can see that the ACF graph is tail off and PSCF graph is a cutoff at leg 1, which indicates that AR order is 1, which matches our finding from the JPEG table. This is my JPEG table with highlighted NA and NB values. Estimated parameter and standard deviation using LM algorithm. States model ARIMA process for option A and B are this. Note that I have included seasonality, and looking at the estimated error variance of error for order B, that is 107.043, which is less than order A. So using this is a ARIMA model summary. Using this model, the forecast function from states model ARIMA, I have generated this forecast. From the plot, I can see that the seasonality index is approx 52, and from the plot of weekly data versus forecast, I can say that the test data and the ARIMA forecast is quite matching at some extent. Now let's talk about residual analysis and the diagnostic test, wherein I can see that the residual is white, and this is the estimated variance of the error and the estimated covariance of the estimated parameters. Let's check if our derived model is biased and it is biased with some error, and these are the variance of residual and the forecast error, which is less than residuals. Let's check if we can make use of model simplification, but looking at the values, I can say that there are no common roots, so we cannot apply this to this model. Now let's check the performance comparison of all the models that we have seen so far on this data set, and from the table I can see that the existed R-square method is the best forecast method using linear regression. Now let's talk about edge step ahead prediction, and from the plot I can say visually that the prediction are matching the seasonality pattern of the dependent variable. In the plot of the test data, there are some values around 202107 are too high as compared to other Christ in the test data. I can see that the prediction is not matching well for this part, but otherwise this model works pretty well. So let's check our dashboard that I have created, and this is a list of dependent and independent variable along with the seasonality test which have rolling mean and variance and ACF graph with different legs which is getting changed. Now this is a basic forecast plots having 4 base models, and then there is a halt winter forecast plot where you can change the plot by changing the value, and you can see the difference in the plot. Okay, then there is a multiple linear regression model wherein I have removed 3 features, and the plot gets changed by adding more features to be removed. Then there is a p-value based regression model where again I have removed some features, and this plot we can check by adding more features, by removing more features, and you can see the difference in the plot. And then there is a third model, that is VIF based regression model, which works in a similar way. Then we have our JPEG table and the ACF and PACF plot with different legs, which by which our plot gets changed. And you can even change the value of J and K from here and see whether the JPEG is getting changed or not. And here you can see it is getting changed. So our dashboard is working pretty well. So let's check our last plot. And it's going to take some time. And here is our last plot, IMO forecast. So our dashboard is working pretty well. So let's complete our presentation by talking about summary and conclusion. So in future, I can predict the dependent variable accurately by combination of adjusted R-square and p-value, and see if there's any comparison with the VIF model. The linear regression model was found to be more successful in predicting ozone AQI values based on time series analysis of AQI dataset, air quality dataset. While the linear regression model exhibited strong performance, there are opportunities to enhance using different models. For instance, ARIMA and SARIMA models designed to capture time series dependency may benefit from further fine-tuning and addition of further data using weakly sampled set in the presence of seasonality. And I can say that the deep learning model is going to benefit for further forecasting capabilities. And these are the references that I made use of. Thank you so much for listening, and I hope you liked my project. Thank you.